Now that we're in Chapter 2, which is Introduction to Functions, and the course is also a function course, we should probably start to look at what the word actually means. So our definition here, a function is a relation that creates no more than one output. We'll highlight these keywords in here for any given input. Functions come in many forms, and we're going to discuss them through the lesson today. So let's first look at one of our basic equations of y equals 3x plus 2. This is a linear equation, if we recall, for two reasons from grade 9. First of all, it's an mx plus b form, and the other reason is it's said to have a degree of 1. That means that the highest exponent on a variable right here, remember that variable has an exponent of 1 on it. Just clean that up a little bit there. All right, so now that we've recalled some of our terminology, what if we were to take our x value and substitute 5 in place for it? So it would look like this. 3 times 5 plus 2. So if we go back to our definition and we're thinking about equations, we have to ask ourselves, what value is the output and what value is the input? Our final answer to this question is 17. So we say that our output has a value of 17 and our input has a value of 5. And it makes sense, just as sort of the words mean, the value that you are putting in to x is your input, and what your final answer is your output. So now that we have those two words distinguished, let's go through our definition once more. It's a relation that creates no more than one output for any given input. So what this means is when I substitute in 5 into that equation, it's only going to give me one possible answer, not 2 or 3 like some other equations might do. So we know for linear equations, they must be functions, because for every input, every x value you put in, you're only going to come up with one answer. So we've answered this here. Which variable is our input? Our input is our x value, and our output is our y value. So let's look at this as if it was graphed. So the first graph of y equals 3x plus 2 would be a linear graph, and it would look like this. If we built the whole table of values and graphed it on graph paper, we would end up with a straight line. So let's just even sort of form a grid here around it. So what we can see is for every x value down here on the x-axis, it only matches up and aligns with one y value. There's not two cases or two outputs after you put in an x value. We can look at this also as far as quadratics that you did last year. Parabolas like this. Again, for all of your x values, there is still only one y value. There's never two. Let me show you what I mean. For example, what if we had a graph that looked like this? Now this is not a function, because for this x value here, if we go up, there's a y value there. Let's say that x is 3. So it would have an ordered pair there. And if we went up further, it would also have an ordered pair there. So if this was 4 and this was 5, there's an ordered pair of 3, 4 on this graph, and there's also an ordered pair of 3, 5. So anytime your x value is aligned with two y values, it's no longer a function. We also check our functions through something called a straight line test. And that's pretty easy to do on any graph. So if you look at your graphs, and you can draw straight lines with a ruler, straight lines there, all the way through, and it only touches your graph once, then it's a function. It passes the straight line test. Where here, when we make a straight line vertically up and down, that fails because it has two output values for each input. So this one here, this example over here, is not a function. The other two are. So we've looked at how to tell by equations which graphs are functions and which aren't. And now we need to look by coordinate pairs. Also table of values. So that's what these are here. Our table of values are here. Remember that for your table of values, the pen back, these are just ordered pairs. So that's an ordered pair on the graph at 2, 4, 3, 5, 2 and 6, and 3 and 7. So as long as all of your inputs only have one output, then it's a function. But in this case here, we see that we have one input of number 2, your x value. X is always your input. You have one x value, but it produces 2 y values. So that would not be a function. Let's pretend that's a straight line on a grid. So if we had 1 and 2, that point here could be an ordered pair 2, 4, and this one here is 2, 6. So if these were graphs on a grid, they would fail the straight line test because as soon as you went through them, it touches twice, and each straight line can only touch once. So therefore, this one here is not a function. If we look at our second table of values here, all of our x values, all of them there only appear once. So this is a function. So for every x value, every input value, it has its own separate y value. Now mapping works a little bit different. It's the least used one, but we'll still show it to you. It appears in your textbook, but mapping is often bubbles like this that have values in it. Let's say 1, 2, 3, and then a bubble over here, 1, 5, and 9, and it shows you arrows across. Just think of these as diagrams for tables of values. The end with no arrowhead is your x values, and your end with the arrowhead is your y values. So they're much like ordered pairs, 1, 1, 2, 5, and 3, 9. So as long as all of your inputs, all of your x values still only appear once here, then you know that you do have a function. So this here tests that it is a function. We say functions now and write equations a little bit differently now that you know what the word means. So we often use an alternate notation. For example here, f at x, g at x, h at x, it doesn't matter, any letter. We now use that in place of y, which you can see here. And we say it as f at x, or in this scenario here, g at x. The reason we do this, so let's go back and say we are substituting in 2, and for x, we have 3 times 2 plus 2. It shows us what we substituted in. This way, using this notation, we know what our input is. Because when we have a final answer, f at 2 equals 8, we know that when x is 2, our y value is 8. Compared to our old way, when we used to do 3 at 2, when we came up with a final answer of y equals 8, when we just looked at the answer, we had no idea what x was. So by using function notation, we can tell what the input is and the output in the final line. Now let's look at some functions that we have here and some examples how to put our inputs. So we first realize here we have f at x is our one function, and we know that it's linear. And we also have a second function, g at x, and we know that it's quadratic because of the x squared. That has a degree of 2. So let's just clean that up now. So we have two different equations. So when we solve an input, it's really important that we look at what function it's asking us to solve for. So our example A tells us to go to the function f and substitute in 1 anywhere where there is an x. So we have negative 2 times 1 plus 3. I have too many equal signs here, so I want to be sure that that goes away for communication. We never have two equal signs. So our final answer of f at 1 equals negative 2 plus 3, and then f at 1 equals positive 1. So what this tells us here is when we substitute in x, our y value, substitute in x a value of 1, our y value is also 1. So we can think of that as an ordered pair, 1, 1. Now when we move to our next example, it's important to realize we're substituting into the g function now. So we have g at negative 2. So we write our notation properly now. And then we have negative 2 squared plus 1. So g at negative 2 equals positive 4 plus 1. Therefore, g at negative 2 is equal to 5. So this shows us in the last line, when x is negative 2, y is 5. We can also, again, if we want, think of that as an ordered pair on a graph. All right, now we have an example here where we have g at 3 subtract g at 2. So the first thing we have to do is figure out what g at 3 is equal to. Then we have to figure out what g at 2 is equal to, and then we take our final answers and subtract them. So we'll show you here, our first one is 3 squared plus 1. So that's g at 3, subtract, and the brackets will help you with your order of operation, keeping things organized. Then we have 2 squared plus 1. It's really important that we solve our two functions first before we do the subtraction. That's the last thing. 9 plus 1 equals 10. Subtract 5 for a final answer of 5. So our g at 3 subtract g at 2 is equal to 5. That's different than this one here. This one's actually much more simple and not to be confused with the other one. You can simplify it right away and just put g at 1, 1 squared plus 1, and solve it right away. So you're not dealing with the two different values. Our last couple examples here for this video, and then we are done for today. It's important to remember things like order of operation. So what this says here is that you are going to double the f at 3 function, or take the f at 3 function and then multiply it by 2. So we first have to figure out what f at 3 is. Let me erase that. So we first need to know what f at 3 is equal to, and then we will multiply all of it by 2. So f at 3 means negative 2 times 3 plus 3. So we leave that 2 until we know what that whole f at 3 function is, which is negative 6 plus 3. Then we have 2 multiplied by negative 3 for a final answer of negative 6. So doubling the f at 3 function gives us a final answer of negative 6. Same thing here. That's 3 times f at negative 2 plus 8. So we just have to be careful of our order of operations as all this is going through here. Excuse me. So we have f at negative 2, so that makes negative 2 times negative 2 plus 3. We'll multiply all of that by 3, and at the very end we'll add 8 to it. Remembering BEDMAS, very important. So we have positive 4 plus 3 plus 8. 3 times 7 is 21. For a final answer of looking at graphs and trying to answer what our functions are. Keep in mind that when we see that we're looking for what f at 4 is, that's still saying what is the y value when x is 4. So our grid numbers are hard to see here, but just all of the lines are increasing by 1. So if we're looking for f at 4, oops, right here, that's 4. 4 lines over. So when x is 4, we're wondering what y is. That dot there, so we read across, over, 1, 2, 3, 4, 5. So when x is 4, we know that our y value is 5. That's the ordered pair, and that's what it's asking you for. It's asking you for the y value. Again, if we're saying function at -2. That means when x is -2, right here, that's where x is -2, what is our y value? -1, -2, -3. So when x is -2, y is -3. So that's what they're asking for. So if we were to answer that question, f at -2 equals -3. We'll do this one here too. F at 4 is equal to 5.